Hi everyone, this is Joe. Today let's talk about the state machine and how we can analyze the sequential circuit. By definition, a state machine is a synchronous sequential circuit. If you remember last time we talked about synchronous counters and shift registers. So both of them are a type of state machine. Okay. So first, a state machine must be a synchronous sequential circuit, and it consisting of a sequential part and a combinational part. So the sequential part, we have another name like the memory part. So it can remember the previous states of the machine. And the third, the output and the internal flip-flops progress through a predictable sequence of states in response to a clock and other input signals. So we can see that in a state machine, the output also has a fixed pattern. It always goes through a sequence of states and go back to its initial state after it goes through the last stage. Okay, so very similar to the counter. So that's why it's very important to understand the synchronous counter. It can help us understand this general state machine. Okay, and there are two types of state machine. The first one is known as Moore state machine. In a Moore state machine, the outputs are determined solely by the present state of the machine's sequential part. In another word, the output is only determined by the memory circuit, or like the output of flip-flops. Okay, and the other type is known as the mini state machine. In a mini state machine, the outputs are derived from the combinational section and the sequential section. Okay, and I put two diagrams here to help you understand. So you can see in the Moore state machine, the output directly come out from the memory part. But in the mini machine, the output, some of the output come from the memory, but there are some output also come from the combinational logic or the combination of those two. Okay, so that's how you differentiate it. For example, the gray code counter we designed in previous lecture is a state machine because first, it's a synchronous circuit. Synchronous means all the flip-flops share the same clock input, right? Second, in this circuit, we have the combinational part and we have the sequential part. And third, the output Q2, Q1, Q0, they go through a fixed sequence of states, right? That counting in the pattern of grain code and over again. Okay, so this is a state machine. But is it a Moore type or mini type? So depending on the definition for Moore and the mini machine, we just need to check the output, right? So here we only have three output, Q2, Q1, Q0. So they are the output of the flip-flops, which is the memory part. Now recall the definition. If all the outputs come from the memory part, it's called Moore machine. So this grain code counter is a Moore machine. Actually, most of the synchronous counter we talk about, they are Moore machine, unless we add more output to them. And we will show you how to do that. Okay. In order to understand the state machine, we will still use the state diagram. But this time we will add some control input to the state diagram. So first, some terms. A control input is an input to the state machine that helps direct the machine to make transition from one state to another. Okay, and depending on how the state makes transitions, we have conditional transition or unconditional transition. In a conditional transition, which means if we want the state machine transit from one state to another, we need to give the machine a control input signal to make it happen. So that's called a conditional transition. The control input value could be 0, but it also could be 1, depending on the application. However, for unconditional transition, the transition just happens, no matter you give the control input signal or not. Because this always happen. But there's another kind of condition didn't mention here, is that no matter in conditional transition or unconditional transition, the state machine always need an active clock signal to make the transition. So when we say the state machine make a state transition, which always means there is an active clock signal coming in, so it can make the transition. Because think about it, there are flip-flops in the machine, right? The flip-flops only change states when the clock edge comes, either rising edge or falling edge. Okay. And state variables. So we use binary variables or Boolean variables to represent this different state. For one bit of data, we can represent 2 states, right? So one flip-flop can represent 2 states, 0 or 1. Okay. If we have more than 2 states, we need 2 flip-flops or 2 state variables. All right. So let's look at a simple example on the right here. So we have a machine, but we represent it using state diagram. And in this machine, we have 2 states. The start state, which we use binary 0 to represent, and the continue state, we use binary 1 to represent it. Okay, and this machine will make transition between these 2 states depending on different situation. And here is how to make the transition. So say we start with the 0 state or start position here, and we have a control input called in1, and we have 2 controlled output, out1 and out2. So these 2 outputs are extra outputs besides the flip-flop output. Okay, because we use the flip-flop outputs to represent the states, right? So we need 1 flip-flops here. And when the control input equal to 1, and let's say we are here, okay? So if the control input is 1, you can check this one here because we follow this format. So use the / sign here. On the left of the slash, we put the input. So when the control input is 1, when we look at this machine, we can follow this arrow. We can tell that at this moment, the next state is pointed to itself. So which means it won't make transition in this condition. Okay, and the 2 controlled output is 0, 0. However, when the input is changed to 0, we can find 0 means this arrow here, which means the state will make transition from start state to continue state. And at this moment, the 2 controlled output will be set to the value 1 and 0. Okay, next, if we are here right now, if we are at the continue state or state 1, and this time when the clock edge comes, it doesn't matter what happened to the input because it use x here, so x01. X means don't care, so it doesn't matter whatever value we put there, it always makes this transition. So this is an unconditional transition. It always happens whenever there is a clock rising edge. If we are here, it always go back to the start state. Okay, so that's how we understand this state diagram. So once we know the state diagram, we can figure out the state transition table. Okay, so let's see. So PS means present state, NS means next state. Input is the control input, and we have two output here. The synchronous input here, basically, this kind of depends on which flip-flop you want to use for this state machine. So here we use this easiest one, use a D flip-flop. Okay, and then let's try to figure out this table. So if current state is 0, which means the start state, and the input is 0, now from this state diagram we know that it will make transition, right? So next state would be state 1 or continuous state, and the output will be 1 and 0, and of course D will also equal to 1 because the D equal to the next state. Yeah, if you don't remember this, go back to our last lecture, okay, and find out. Okay, if current state is 0 but the input is 1, check what will happen. It will stay there, so which means next state equal to current state, present state. And so D should also equal to 0, and the output is 0, 0. If current present state is 1 and the input is 0, because this is an unconditional transition, so it doesn't matter what happened to input, they should be the same. So the last two states should be the same. Always point back to state 0. So D should be 0 too. The output will be 0, 1, 0, 1. Okay, so this is how we figure out the state transition table, and this is critical for designing a state machine. Now let's look at some more examples. Okay, say we know the state machine. Okay, then we just need to figure out how to realize it using logic diagram. Okay, so we need to translate this state diagram to a real circuit. How to do that? So we have this machine and we know how to read this, right? So we have 3 states here. That's why we need 2 state variables, which means 2 flip-flops. Okay. Then the states make there are transition among those states depending on the input X, and we have a controlled output or asynchronous output Z. Okay, we call this Z asynchronous because it doesn't necessarily depend on the clock signal. Okay. Now let's try to figure out the excitation table. Say we have present state 0, 0, do we? So we have this state here. If the input X is 0, we will see we have the arrow point to itself, which means the next state is the same. And the Z output is 0 in this case. If current state is 0, 0 and X equal to 1, we find the arrow, which is this one. So next state would be 0, 1 and Z would be 0. If present state is 0, 1 but X equal to 0, we can find this arrow here. So the machine will make transition to state 1, 1. and z is 0. If x equal to 1, you can see it's go back to itself, so nothing changed, and z is 0. If we are at state 1, 0, however, this state is not showing in this machine, right? It's not there. So how to deal with that? Basically, it's not there, which means first, we don't know its value, and also we don't care its value because it's not inside the loop. No matter what value we put here, it shouldn't affect this machine right now. So the next state actually is don't know or don't care, and we don't know z value neither. If present state is 1, 1, and the input is 0, we can see we have this transition to go to 0, 0, and the z is 0. Finally, if x is 1, we go back to 1, 1, and this time z equal to 1. Okay, so now we have this state transition table, and then next step is to figure out the Boolean expressions for the next state. So Q1, you use plus here, but we can use n plus 1, but doesn't matter. So let's just use plus sign here, mean next state, and the z. So we have 3 output, and we have 3 input. So we have Q1, Q0, X. Q1, Q0, X. Q1, Q0, X. Okay. So we have Q1 plus 0, 0, 1, 1, 0, 1, 0, 0 is X, 1, 0, 1 is X. So we have 0, 1. Okay. For Q0 plus, we have 0, 1, 1, 1, X, X, 0, 1. For Z, we have 0, 0, 0, 0, X, X, 0, 1. Okay. Then what do we do? Just using solve the column map. So in this case, we will do that. And for this one, just itself. So Q1 plus should equal to Q1 prime, Q0, and X prime. Or this one, we got Q1, X. For this one, we have this group, if you remember how we solve column map. So Q0 plus should equal to Q1 prime, Q0, or X. And the Z, we have this. So Z should equal to Q1 and the Z. Okay, but I think I didn't put a thing clear here, is that actually this column map is not for the output Q1 plus and Q0 plus. It's actually, if we use D flip-flop, this should be for the input of the flip-flops. Okay, it's D1, D0 if we use D flip-flop. And if you use other flip-flops, you need to add columns to figure out the input value of the flip-flop. Okay, so here we just still assume we are using D flip-flop. These are most commonly used ones. Okay, then this should not be Q1, neither should be D1, D0. Okay, so that's a mistake I make. So once we have D1, D0, and Z, this is X actually. Once we have the Boolean expression for D1, D0, and Z, we can figure out logic diagram, right? But one more thing to mention is that, so for this state machine, what output we have? We have output Q1 and Q0, which is from the flip-flops, right? And also we have output Z. So Q1, Q0, they are directly from the memory part, the flip-flops. But the Z, we can tell it's determined by the Q1 value, the current Q1 value, and the X value. So this is a pure combinational logic, right? So this actually is a mini machine because it has an output which comes from the combination of sequential part and combinational part. So this is a mini machine. Okay, now let's look at another example. So in this case, we know the physical circuit here, but how do we figure out the state diagram for this machine? Because only when we know the state diagram or the state transition table, we can understand what this machine does. Okay, so how to do it? So the first step, we get all the information we can from this logic diagram. So first, we can write the Boolean expression for Z, right? Let me rewrite it. So Z should equal to, so it's an XOR gate, the input coming from the output of the two flip-flops. So it comes from A XOR B, right? And also we need to figure out the input for the flip-flops. So dA equal to X XOR B prime, and the dB is equal to X or A. Okay, so that's all the information we have for this logic diagram. Then but that's enough to figure out the state transition table here. So if the present state is listed here for the two flip-flops, and X is a combinational input here, or control input here, DA/DB is the input for the flip-flops. Next state, A plus, B plus means the next state, okay? And we have output Z. And we can tell the Z is actually from A and B, from the flip-flops directly. So this is actually a Moore machine. There's no combinational part for Z. So if current state is 0, 0, and X is 0, what's the next state, and then what is DA/DB? So DA/DB value we can get from the Boolean expression here. So X is 0, B is 0, so B prime is 1. So 0 XOR 1, we get 1 here actually. And for DB, we get, so we got a 0 or 0, we get 0. Next one, 0, 0, 1. Oh, sorry, I forget Z value. 0 XOR 0, we get 0. Okay, and the next state, because the next state for the D flip-flop equal to D, right? If you remember, so this also 1, 0. And the next 0, 0, 1. So 0, 0, 1. So 1 XOR 1, we get 0. And 1 or 0, we get 1. So this will be 0, 1. And the Z will still be 0. 0, 1, 0. So which means B prime will be 0. So this is 0 XOR 0, we get 0. And A is 0, X is 0. So we get 0 here. So we get 0, 0, and now 0, 1. So this z will equal to 1. Yeah, actually, it's get faster if we do column by column. So let's figure out dA first. So dA is x or b prime. So 0, 1, we will get 0, 1, 0. Oh, sorry, 1, 1. We will get to 1 here because this is b prime. 0, 0, we will get to 1. 0, 1, we will get to 0. 1, 0, we will get to 0. 1, 1, we will get to 1. Okay, for dB, x or a. So compare these two columns. So if they are different, we will get to 1 here. If they are same, we get to 0. Okay, then this just follow D. So we have same. For Z, A, X, or B. So compare the first two columns. If they are different, we put to 1. If they are same, we put to 0. That's it. Okay. So then we got the value for present state and the next state, depending on the X input. And we have Z value too. Now we are ready for the state diagram. But the first thing is to determine how many states we have, right? So we have 2 flip-flops, which means we have 4 states maximum. But how the transition works, that depends on the X, right? So if when we are at state 0, 0, or state 1, you can call it 2, 0, state 1, 2, 3, you can call it. If we are at here and X is 0, we know the next state is 1, 0, which means this will transit to here, and when X equal to 1 and Z equal to 0, right? And again, if we are here, but also X is 0, X is 0. If X equal to 1, next state is 0, 1. So we are going here if X equal to 1, but Z equal to 0. Okay. If we are here, so if we are here and X equal to 0, the next state is 0, 0, which means if X is 0, we'll go back and the Z equal to 1. And again, we are here, but X equal to 1. Next state is 1, 1. So it moves here if X equal to 1. And the Z also equal to 1. Next, 1, 0. If we are here now, maybe I use a different color. If we are here, 1, 0. If X equal to 0, next state is 1, 1. So you point to that. And the Z is still 1. Okay. If we are here, but X is 1, the next state is 0, 0. So you do this. X is 1, and Z is 1. Next, so if we are here, but X equal to 0, next state is 0, 1. So this will move here if X is 0 and Z is equal to 0. If X equal to 1, next state is 1, 0. So actually we'll move here 1, 0. So that's the state diagram for this machine. Okay, it's not very straightforward what this circuit actually does, if there are any physical application for a machine like this, but that's how the state diagram looks like for this machine. Okay. Okay. So finally, let's look at one more example where the circuit do have some physical meanings. So this is a serial AND circuit. If you remember when we talk about the ANDers, and we said we can use the 1-bit ANDers for ANDer to cascade it to make a multiple bit ANDer, right? That's a parallel configuration. But in this case, it's a much simpler configuration. We only need one for ANDer and one flip-flop. We can do the addition. But this time, all the data feed in serially. Okay, one pair of bits at a time. So to be simple, how this works is that we have the first bit of data, or the LSB, two number fit into the for-ANDer, and the D flip-flop will be reset initially. So this xi plus, or you can call it x0, y0, because this is LSB, right? This for-ANDer will add this lowest two bits together to result sum and carry bit. Okay, then this sum bit will be saved somewhere, and then the input will be updated. Okay, and the carry bit will also be updated using this D flip-flop when the clock edge comes. Okay, so then this for-ANDer will add the next bit with the carry input. Then the next bit of data will be saved again. So this process continues until the final result is obtained. Okay, so pretty simple. So since this is a state machine, so let's look at how it works using state diagram. Okay, so let's try to translate this logic diagram into a state transition table. So because we are adding like two numbers holding here. So let's say initially xi and yi equal to 0, 0. Okay, because for xi, yi, they're only four combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Right? But we have an actual input, which is the carrying input, ci. Okay, so if xi, yi equal to 0, 0, ci equal to 0, because it's a for-ANDer, very easy, so you get 0, 0, right? 0, 0, 1, you get 0, 1, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. Basically, this is almost identical as the for-ANDer. Okay, but you should know that because ci plus 1 here is connected to the D input of the clock. So this is actually tells us the next state and the D values. So once we have that, we can do it. So how many states we have here? We have one flip-flop. So we only have two states, 0 and 1. And how they make transition? But we have like how many input? We have two control input, xi, yi. Ci is actually the Q output. It's a present state. Okay. So it's used as input. So this part is the input. This part, this two is output. Okay. So the input is xi, yi, and we have asynchronous output si. Okay. So if xi, yi equal to 0, 0, the next state is 0. And if the ci is 0, so what will happen is if present state is 0 here, it will go back to itself. So 0, 0, and si is 0. Okay. If present state is 1, but xi, yi equal to itself, the next state is 0. So what will happen is this when 0, 0 happens and si equal to 1. Okay, now the third line translating as if we are at state 0 and xi y equal to 0 1, the next state is still 0. So it still go back to itself, and it's 0, 1, and si equal to 1. And the next, if we're at state 1 and xi y equal to 0, 1, the next state is still 1. So it go back to itself, and then we get 0, 1, output is 0. Next, if current state is 0, but x, y equal to 1, 0, the next state is still to itself. So it's 1, 0, and the output is 1. Okay. And if current state is 1, and we have 1, 0, next state is still 1. So we have 1, 0, 0 this time. Lastly, if we are at 0, but we have 1, 1, it will point to state 1. So 1, 1, 0. And the last one, if we are here, and it's 1, 1, it stays to itself. You don't have, but you can also write this so the second condition that results in pointing to itself is 1, 1, 1. You can use a colon or comma to separate these two conditions, which means actually these three conditions have the same result, just go back to itself. You can write them using one arrow or three arrows, doesn't matter. Okay, same, as long as it tells the same thing. Okay, so that's it. Okay, basically that's how you can do some quick analysis for a given state machine. And in next lecture, we will talk about how we can design some real state machine that has real world application. Thank you.